So last time we discussed the more general finger-headish action, where apart from this, let's say, phi R and phi L parts, which had the field definitions for the upper and lower branch of the finger-headish contour. This will be the case for a unitary QFT where there is no mixing, although the in vacuum is not equal to the out vacuum, so we need to, in such a case, we need to use the finger-headish formalism, but the entanglement structure doesn't change and it stays a unitary evolution. So there is no mixing term. However, in case of non-unitary evolution, for example, open quantum field theories, you have a influence functional, which is called Feynman-Vernon influence functional. It should be a mixed term of phi R and phi A. And we wrote down also the form of this influence functional. We discussed an example and further, basically starting from the GKSL equation, we showed that if we take the path integral version of the GKSL equation, we get this Feynman-Vernon influence function, which is something like there will be one mixed term. But it will also be pure phi R and phi N terms. They come naturally if we try to derive from the Feynman-Vernon GKSL equation. And capital.
So you're writing this influence function and some formulas.
Yes. They are just the L operators you can again think of as similar to what we had in the GKSL equations. So the operators in the interacting part of the Lagrangian, there will be also a, after let's say integrate out some degrees of freedom. So for example, I could start from the example I discussed last day. Let's say I have a q degree of freedom for which I have Lagrangian in this term. Then I have a x degree of freedom, and I have a qi kind of interacting part with some coupling also. You could associate a coupling with this part. Now, if I write down the whole unitary finger-headish action for this thing, that will just be s phi r minus s, not really s phi r, but sq minus sx kind of thing. But if I then integrate out the degrees of freedom corresponding to x, then I will get a, actually that will give me a doubling of q as well, q and q prime, and at the same time I will have a functional here, influence functional determinant of mixed kind of term, which is both function of q and q prime. And that term in general is just, I haven't seen a very complete derivation here, but that term starting from a, on the other hand, we start from this description and write the GKSL equation for this description and write the path integral version of that equation. Then we will see that this L prime, L dagger and L are nothing but the L that we had in the GKSL equation. This finding space. So today we will not need much of these, so we will discuss something else which is basically called the Weltman cutting rules. So if you remember, we discussed, okay, let me start from there that in a finger-headish from a finger-headish contour, we actually had 4 kinds of correlators. So this is my first kind of rotator. Let me write this as GRR. Then I will have this is time order, because this is in the upper branch, that is forward evolution. In the lower branch, if we take, then this will be anti-time order. This kind of correlators. So I write as GLN. Let me write this way. This means anti-time ordering. So just change this part. And there were two correlators. And this one. So I write this as GRN, because we are starting from R. In the contour, we are starting from R and P. There will be no time modeling in this course. And these two are also on-shield proprietors, which has to, because this has to cross this boundary where these are identified, which equals to its line. Now let's discuss a very simple example, which is free scalar field theory. It's still unitary and everything. There is nothing non-unitary going on here.
There is no time for the last
No, but whether T1 and T2, I am writing here says that the inside here will not, you consider all kind of terms, no time ordering. But here, let's say this one is T2, this one is T1, and here it is T1, T2. Still contour ordering is there. That's why I have written it this way. Contour ordering means I am going from here to here to this path. Here everything is actually contour ordered. I have divided it in 4 terms, one of which is I can write in terms of simple time ordering, one of which I can write in terms of simple anti-time ordering. But the other two is still I have to, while performing the integral, any integration, I have to firstly insert the operator at T2, then find backward flowing, I have to insert the operator at minus T1 and so on. No, this is not time ordering. That's what. This is not time ordering because this is forward evolution, this is backward evolution. This is kind of mixed in time code. Just this p square plus m square usual. So what is the question? Usual on-shell. So the computations that we have to do in case of a, let's say, free massive scalar field theory, we have to do it. Yes, I will compute that. Yes, exactly. Exactly. There will be a delta k square plus m square. Yes. Yes. So, say for a scalar field theory, position space will be this. And in momentum space, this action can be written as this. Fourier transform. So this tildes are again the Fourier transform version of these 5 R's space. And if we put some, because we want to maybe we want to get the, do we want to get this? This is the Green's functions by basically if we write in terms of some phi r, phi n, and whatever in this action I get in between here, taking the inverse of that I can get the Green's function. So for that to get the Green's function, I try to write it down in a way where I have already suitably introduced the IXM description. And this as we already theta functions here, and simply these theta functions you can already see from here. We will get the, when you take the inverse, we will get the delta functions. So basically, if we identify, say, if we got this matrix A, E as the inverse of Green's function. Then my Green's function will look like this, the inverse of that, which I can just write in this form. the off-diagonal terms I'm using theta functions such that these theta functions will be introduced. So they were so these theta functions are introduced such a way that if you take any phi r, phi l, etc. So if you take that fraction has to go to 0 if we identify phi r going to phi l at any point of time. So I have not derived this, but the justification of taking this theta function is that fraction identified to phi l. In that case, this now, if you look at this Green's function, my GRR will be this. GRR. Yes, yes. You have to just again, this is sort of put by hand, but again, you have to take this finger candy section and you have to make sure that at any instant of time, if you take phi r going to phi a, it has to go to 0 and good that is going clearly to 0, but you will have to insert certain other terms, some off diagonal terms to make a sense of that, such that it is it is well defined as a contour order integration as well as when you take. Yeah. I have not done the precise derivation, but I will do the derivation of that. I have not taken about the steps in between. So this is GRR, this is JL, this is like GRA, and the remaining level is GLR. This was one example of this will come. So another fact that we can check this one, check from this GRR, GLL, and all of this. Also from these things, we can use all of these to show that GRR plus GLL will always be equal to GRL plus GLL. This is true in general. This can be shown from this itself, but from those expressions also. So this is important to remember. So this we will come back to later. So question number 2 is start. So now basically what we want to discuss is by looking at quantum field theory or studying a quantum field theory, how do we know or how does one check whether it is unitary or not? So the unitarity check that we will be discussing is through something called the starting rules. The starting point is that is the starting point is the optical theorem, but again we can write it in other ways. We know that for our initial state and even initial and final state, I can write scattering matrix element in this way. And if it is so, this should be unitary. Conserve probability. So if the general exponent is I write in this way for and say that this has to be followed. This is dagger towards to identity or this dagger is this and using this definition of case we can get that the transition matrices has to follow this idea. And so what we usually do in our quantum field theory is in the description of doing it in terms of the Feynman diagrams, order by order and so on. So it is a quantitative description that we usually use, and there it is not very trivial. This statement is not very trivial. We cannot assume this before that. We have to quantitatively check whether in each order this is satisfied or not. And so this has to be checked order by order. And we'll say something that we came to in the advanced part of the quantum field theory courses was, let's say, if we start from some 2 scattering, that is the initial state is the particle state as well as the final state. And so this is first step in between T dagger and T in this right hand side part, T dagger introduce, we have to introduce identity in terms of arbitrary or many particle states. The completeness of the 3 particle states. This expression in terms of friction and final states. This part and y. This can be written as. Okay, so now if we just use the fact that this kind of identity, so T is multiplied by T with the scattering amplitude from K1, K2 and this T is multiplied by some multiplied to the power 4 delta 4 K1 plus K2 and the sum of 3. Then this equation, it boils down to the following equation. different part. Again, just this part. This I call some. Then one start. One people going to into, so in the left hand side I have gotten rid of one such delta functions already, so in the right hand side I have one delta function. And so for forward scattering we will also take this P1 or Pi is equal to Ki's. Then this equation actually, the left hand side becomes only the imaginary, something multiplied by the imaginary part of the which is scattering amplitude, and in the right hand side we get something multiplied some energies in the center of mass plane, momentum in the center of mass plane, and some scattering cross section. But in the most general case, this is the expression where I haven't, I'm just not considering not just the forward scattering or Pi going to Ki scattering, but this is for general equipments, general to scattering. This is, sorry, from here you get M. No. After this, I'm in the left hand side thing also I have to consider where this kind of expressions will appear, single M terms. And yeah, so from one you will get M, from P dagger you will get M star, and in the right hand side you will get multiplied by two such scattering amplitude multiplied. So what this means is that we are doing something of this sort. K1 K2 is going inside, so K1 K2 is coming outside. There are some, I don't know what is exactly happening here. I'm basically reacting with this values kind of figure out this, but all following all possible failures where this part of that we consider, but the X are in this line that is going here to be any multiple things. K1, K2 go inside, and I get multiplication with this kind of thing. Finally, K1, K2 go K1, K2. So this things in terms of Feynman diagrams were shown in terms shown checked order by order successfully. Firstly, this is a bit of history. So in lambda 5/4 theory, interacting theory, the Feynman diagrams shown to satisfy unitarity. And when I say satisfy unitarity, of course means order by order. This was shown by Bhattacharya through some rules which are known by Bhattacharya cutting rules. In QED it was shown by Feynman himself, and in spontaneously broken gauge symmetries examples, for example, network interactions. This was shown by proof and this PhD advisor. In fact, this particular work, due to this work, they got the Nobel Prize. And so we will discuss basically this will not, cut-off rules are very similar, but we will not go into those details. Those will not be necessary to discuss this Whitman rules. And so we will discuss this part. And of course, we will get to some equation by looking at which one can say whether a theory is unitary or not. For example, by looking at this type of equation. This equation, we will see that we will get exactly this equation starting from the Whitman rules, and this equation will be true if the unitarity constraint is satisfied. So this equation will hold only for unitary finger-gauge procedures. If we have a influence functional where the procedure is non-unitary in general, this equation will not hold true. I have not got that bit. Right.
So those will be both necessary and sufficient for unitarity.
Probably it's not right to say this condition is necessary and sufficient because we are going to check this only order by order and we are not doing any non-quadratic calculation through which we can make such a stronger statement. But in some sense, also holding, so in general, one could say that this has to be true in the non-quadratic sense. But if we can already show that in the unitary theories, this holds order by order in each order, then actually this becomes a little stronger statement itself. The condition of unitarity seems that it becomes that it has to be satisfied order by order, but I am not sure particularly if there is a situation where in some order it is satisfied and in some other order it might not be satisfied. That depends probably on the order of the influence functional that you have in your finger-gauge connection.
So only the relevant orders will concern us in what we are doing, right? And just say for the first few orders, it is unitary.
In general, yeah, probably the general idea is still, although I said that I don't know any examples, the general idea is still that if you check first few orders and if you get there is no violation of this equation, then you assume that it is unitary and you should already see some violation if your theory is non-unitary. So basically we get a simpler setting where I write this equation again sandwich between initial and final states. And then by mighty dagger I have already taken care of this minus sign here. This line means possible physical states. And physical states would be something with negative norm states or negative norm states in these cases. So if we follow this equation, then basically this means that let's say the thing that will come handy before we introduce the precise rules, just remind ourselves with certain things. For example, any Feynman propagator going from y to x, you can write in this way. Basically means the primordial thing. And in fact, well, it says this is something of this kind. This is just like this part. In fact, what we can do is let's situations. This we call the class X minus Y. Then we can sorry?
Yes, I have. You like that box equation.
No, I'm not writing the box equation. I'm just writing a usual finite propagator. This means that I model if x0 is greater than y0, we will take phi x phi y.
Yeah, but yes, I.
Here, this thing, I just this is a different equation that I'm just reminding us with the Feynman propagator. So we'll come back to that later. How that comes from, let's say, the Whitman rules and dealing with such propagators and more general Feynman diagrams. How one can get to that equation that will. Sorry? That equation is still this equation, this part. But the iota has been changed. Yes. In the left hand side you only had K1, K2 going to P1, P2 kind of situation. In between I am when I yeah. Yeah. Yes, that is the optical theory. Imaginary part only I am writing. When I write this kind of equation, what I mean is the imaginary part of this left hand side will be equation. More precisely, probably. So this will be the imaginary part if we go to forward scattering unit. That is K1, K2 going to K1, K2. In a more general setup, it will not be imaginary, but it will be some minus I multiplied by the scattering amplitude. So, but you can also show that this delta plus x minus y, the complex conjugate of this is simply delta minus of x minus y. And using this fact, we can in fact describe an anti-time ordered propagator as well. So define anti-time ordered. It's just the opposite thing. Y0 minus x0 will be phi x phi y and x0 minus phi 0 will be phi y phi x. So the anti-time ordered thing, which will just again be the complex conjugate of this, that propagator, we can write in this function. We just change the things. So delta y0 minus x0 will now multiply theta y0 minus x0 will now multiply delta plus and x0 minus y0 multiply delta minus. So what we will do now is basically here where we have this division between these diagrams, we can have more general such, we don't precisely know what is happening here, so we can have a very complicated Feynman diagram and so on. These are usually called cuts. So what we will do is we will define these cut diagrams in the following way. They are these diagrams. They are on the left of the part, left of the cut. We use DF, that is usual time ordering, and on the right of the part we use star, that is anti-time ordering. And for the cut lines, so here where I am identifying these lines to these lines, there basically we will use this either delta plus or delta minus. And if these are followed, we can get to something called the largest time equation, which we will see in a while. So when I say these things, what do I basically mean? If that is on the left of the part, in this part, we will use this for this kind of things. DF star we will use for kind of things. Remember we had this inserted in the middle this things and some variables. So for this part we will use this DF, or this part we will use the propagators of the kind of DF star, and in the middle where we identify this or join these things with each other, we will use delta plus or delta minus, that is delta plus and delta minus for basically some of the streams that you take from the distinct streams. And now let's erase this and the roots now, the white man cutting roots. Yes.
So initially when you set up this constant right?
Yes.
Then you set it up to momentum space.
Yes. I'll again go back to momentum space later.
Yeah.
So think they are written in terms of, as far as I have seen, they are written in preposition space.
Yeah. So in that case, it's a bit different because
Sorry, in that case,
yeah, in the sense that it seems a bit different in the sense that it is the standard way used to check regularity in case of versus unstandard. So it's a kind of wasted. And so basically the reason I'm asking this question is that basically open problem theories, one usually studies actually population functions. That's what studies are. Yeah, so I'm just wondering that the standard way of checking unitarity the standard language that formalism is appropriate for
I think it seems so because we are not going from the scattering point of view, but we are just the evolution of the quantum system, whether we want to check whether it is unitary or non-unitary. So that evolution is studied from the scattering matrix also. And when you check whether that evolution is unitary or not, that should follow some for. This is actually not only true for propagators, but this is valid for general any Feynman diagram kind of things. So for any correlation functions also this kind of thing should be true if you are dealing with finger Keldish and whether you have a unitary theory or not. That we need to know.
yeah. So in this case, what I was basically trying to point out is that in this context, checking unitarity at the level of actually Green's functions.
No, not that is again what I wanted to do. So I will probably describe it in terms of Green's function, but it is not only valid for propagators. You can take a general in not only in the level of yes.
Yeah, the difference seems to be that like I want to check unitarity for let's say for some functions this correlation function. That in comparison to checking unitarity for some scattering
So if you have for a given theory, let's say even in the open quantum field theories, one would have to deal with to check openness and so on. One has to deal with Feynman diagrams, and order by order, one has to check this whether this unitarity constraint is followed or not. In the open, most open case, I assume that it is not followed, but in that case, even in that case, yeah, position space things you can deal with that just by looking at the Feynman diagram. What you will see is that there is a natural way from this Wakeman rule, so you can just look at the Feynman diagrams, and if you have a plethora of have a full list of possible Feynman diagrams, then you can check already that whether your theory in that order is unitary or not. Yeah. So let us consider Feynman diagram with endpoints. So in the integrand I have some x1 to xn coordinates. And composed of many such propagators. We also have a factor I size imaginary current I that each vertex. In fact, there is also a minus lambda factor which comes from the coupling or what order we are looking at. But since we will only constrain ourselves within a particular order, we will not pay attention to this lambda term. Let's say we are just focusing on a particular ordered Feynman diagrams, and at the end we will have an integration. The point that we can do is from unintegrated Feynman graph, one particular graph, which I am working this way, you can construct another e to the power n minus 1 diagrams. This number I will come to later, but let's first discuss how these extra diagrams are formed. So these are, I'm going to discuss with Whitman and stuff. Firstly, draw circles. In the first diagram, in the actual diagram, we just have vertices, but we don't have any circled vertex or any particular vertex. We will now draw circles to get the extra diagrams. Draw circles around some of the vertices, or starting from we can do one vertex, two vertex, and so on become one. Which are related to this drawing circle is related to actually complex conjugation. So in the cases where that I was dealing with this T dagger and the thing, and replace I by minus I in the circle graph. So again, that minus I comes from this complex conjugation. Remember that this minus is important. So whenever we will have a circle graph, we will have if there is there are two vertices, let's say. If one of them is circle, then I will have a minus sign, extra minus sign. If I have both of them circle, I will have two minus signs. So this will again give me a plus sign. So, and the propagators between two vertices if psi minus xj, this is for lines connecting uncircled vertices. For example, what we have in our actual integrand, if both vertices are uncircled, then we will associate a usual Green's function, that is time ordered Green's function. If star will be for lines connecting, so if both of them are circled, we will have if star, that is the anti-time modeling, and if delta plus, this will be for lines connecting circled xi to an uncircled xj. And delta minus will be for lines uncircled xi to a circle based. Such that we have all kind of combinations powered through this four kind of coordinators. In fact, this will also be, if you already can see, this will be the coordinator corresponding to GRR, this will be for GLA, and this will be for different other cases. But in that simple terms, we talk about that.
Are you going to give an example?
Yes, yes, of course, agree. Such things. So let's say now let's try to make sense of this e to the power n minus 1. If I have, let's say, 5 points, in my actual diagram, none of the vertices are circled. So I can circle each of them and get a new diagram. Circle this, get a new diagram. To get this, get a new diagram. Each of those endpoints can either be circled or uncircled. So, two possibilities to the power n total number of diagrams I should have, and my actual diagram is all uncircled vertices. Rest of the to the power n minus 1 cut diagrams by using some circled diagrams I will introduce to this particular version. Now, how do I do this? So, whenever I have location, whenever I have this, these are not circled, those vertices. This kind of propagator going from side to xj. This going to be from side to xj. If I have this star, plus these are arrow because these are not diagonal, but these give me some direction for flow of external energy. In which direction, whether I am going from this kind of graphs, whether I am going from left to right or right to left, which kind of coordinators and propagators I am associating these two diagrams to. So, no, but complex conjugation, when I say this complex conjugation means circling a vertex, of a particular cut diagram. Will mean that we replace the circled vertices via uncircled and vice versa. So if I had this and this circle, the complex conjugate will be this circle. And these are just notations that I find. So by that logic, if I start my original diagram that I had, which was all uncircled, original integrand diagram. The corresponding complex computation of that will be, let's say, all circled vertices. And using this notation, what we can get to is something called the largest time equation. So this is an equation relating the original diagram and the complex conjugate of the diagram. In fact, this kind of largest time equation you can think of as relating any cut diagram to its complex conjugate diagram, but in the most precise sense this is the fact. So what we will assume is that for a given graph, xn for some n as the largest time among all n possibilities. So xn0 is greater than xi0 for all I not equal to n. Secondly, consider among cut graphs two graphs that differ only by the fact that xn is uncircled in one and circled in another. So focusing on only the coordinate where I have my largest time. So now say xn is connected to some other vertex xi. There could be two possibilities for xi as well. It could either be circled or it could be uncircled. So if xi is uncircled, we have two possibilities. Where both xl and xi are uncircled, then we have this kind of thing. And if, so this is both uncircled, and if xl is circled, then I will have one uncircled, xi is uncircled first, but xl is circled, so I will have a delta plus xl minus xi. This minus sign I have just introduced, you can forget about this minus sign if you remember that this has, apart from this, these things, it also has a I going to minus I change as well. That's how this is when this is circled, this is uncircled. But this is circled. Now for xl 0 greater than xi 0, which is the case in our case from the assumption already that xl 0 is greater than xi 0. This will have one theta function which was xl 0 minus xi 0, another theta function xi 0 minus xl 0. The second theta function will go away. This will only be delta plus xl minus x. And this minus sign, if you were just look at it now, basically I can take this part in the right hand side, left hand side, and write this equation in the following way. Both circle diagram and both uncircled, no, so XL circle but XI uncircled, and here both uncircled. These kind of diagrams, remember that I am not discussing here about all other vertices. All other vertices could also have circled or uncircled, but just from this corresponding thing, I can write this kind of a thing, which essentially means that I am associating. So this was my BF, the thing. And for this, I will write something like a minus, in fact for this, I think this is my this diagram. So with the minus sign. If I put the minus sign, then I can make this kind of equality mode. And one of these vertices are uncircled, which is the xi vertex is uncircled, but it stays circled. Now this was for the case where, let's say, if xi was uncircled. Now what happens if xi is circled? So for a both circled graph, we already, let's say, both circled xi and xj, we have a, we discussed that this will be a anti-time order thing. XL minus xi, and if let's say xi is circled but xl is now uncircled, then I will have a minus xi for uncircled. I have a minus xl. They are again related because here again xl0 is greater than xi0, then I will have again only that theta function anti-time ordered term in my previous anti-time ordered expression that I wrote. So this will again be equal to just delta minus xl minus xi. And if I associate this minus function here, so minus of minus, then I can associate two diagrams of this term. This is equal to the left side is circled along such two vertices. So the left side here is for the smaller thing, that is smaller time position point. And so what I basically want to mean is that in all such possibilities, 2 to the power n number of possibilities, you will have two pairwise diagrams which will always cancel each other. This diagram cancelling this diagram cancelling this kind of diagram. And remember that we already had one, our original integrand was all uncircled, and its complex conjugate will be all circled, but they will cancel each other as well. Let's write it in this way. My original integrand was of this form. The complex conjugate of that was of this form, where it is all circled. And I have all other diagrams which were also pairwise cancelled. So this, all of these will sum to give me 0 because they cancel pairwise. These are two terms and these are 2 to the power n minus 1 terms. And if I take this in the right hand side, this last part on other diagrams, then I'll have this kind of equation. And this is for typically the largest time equation. So my original integrand and my the complex conjugate of that, and between all other circled and uncircled vertices combinations, all other possibilities of diagrams that I can make out of it. Now let me just end by giving a couple of very simple examples. So this is true in arbitrary Feynman diagrams. So let's take this vacuum bubble, and this will be equal to one such thing. So the left part this way, this will be equal to both sides. Now, let's consider a further, say, complicated diagram. This is, say, steel. It's greater than all other TNs. So I can say this kind of propagations. If we have these two circles, the diagram that will cancel this will just be, remember this is my TL. Where I get rid of the circle of this largest time vertex. This is another way of writing the largest time equation, that the fact is that such pairwise cancellations will happen. Now, what we do if we don't have any knowledge of which time coordinate is my largest time coordinate. The easiest way to deal with it is what I already sort of described, is that you keep adding circles to it, generate all possible diagrams. They are constrained always in such a way that, let's say I started with this vacuum diagram. And first I had this, and then I got a circle here, and then I had these four. And let's say now we want to see situations. Now we see that, say this is 1, 2, 1, 2, 1, 2. Let's say diagrams are 1, 2, 3, and 4. So in case where T1 is greater than T2, what you can show is that 1 plus 3, so this and this will cancel each other, and 2 plus 4 will cancel each other. Similarly, the second possibility is just T2 greater than T1. Here you will see that this diagram will cancel this diagram. 1 plus 2 will be 0, and 3 plus 2 will be 0. We start from such institutions, will always be able to generate only even number of such things, because the possibilities for each vertices are either it is circled or it is uncircled. Then all such possibilities for different largest time possibilities will be associating what the different diagrams will cancel different diagrams, but ultimately the largest time equation will always hold true. And in the more general situation, another way of writing the same equation is that this will be the equation is there are different conventions of writing these diagrams. For example, there are some cases where people put shades in the direction where the vertex is circled. In that kind of convention, write the first term in this way. So there was nothing circled in this part. Whatever is circled is going to the right side. This is the all circle diagrams, and these two diagrams will be this way. Now the remaining point is just again very simple, that if you look at the correlators that we associated different diagrams to, this was the case where xi is uncircled and xj is the largest time is also uncircled. We are considering the time ordered case. That was corresponding for GRR propagator. If one of them is, let's say, xi is uncircled, xj is circled, then delta plus comes in. And there are other possibilities. The anti-time ordering term comes in here. Further delta minus term possibility comes from when xi is circled but xj is uncircled. So again we have this time ordered propagator, anti-time ordered propagator, and two sort of non-time ordered propagators. And if we just relate this kind of diagrams, or even in the propagator level, if we relate this to GRR, and so on. If other two terms, that is delta plus and delta minus, to this GRL and GLR, then what does this equation mean? Is that GRR plus GLL is equals to minus of GLR plus GRL, and sum of them will again be equal to 0. So that equation is equivalent to sort of this equation, that here I have sort of equivalent in the sense that the minus signs are absorbed in here. The minus signs that were introduced in terms of the Feynman graphs from going from I to minus I, if they are absorbed, then this will hold. This becomes the same equation as the cutting of largest time equation becomes the equation that we already had from the sugarcane distribution. Yeah. So let's say here, and what I am discussing the next day is we can go to, firstly I will discuss just some more, because we have in fact two fields in cases of fingerprint, that is R fields and N fields. We can define a new basis where one of such four correlators will go to 0, which is called the average difference basis, where the fluctuation dissipation can also be studied in a systematic manner. And yeah. In fact, there we will see that the correlation that goes to 0, it will be simply written in this form. The basis will be different, but if we write it in this basis, then that correlator will be of this kind. So this going to 0 is modified by studying that particular correlator in open quantum systems. And if you study that correlator of those fields, then you will be able to say whether this correlator goes to 0 or not. When looking at whether this correlator goes to 0 or not, you will be able to comment whether the field theory that you are studying is unitary or not unitary. If it goes to 0, then it is unitary, because this is being followed, satisfied. Otherwise, it's not. We will discuss that, and probably a bit of one example of open quantum field theory, that is 5-4. 5-4. Yeah.
So this suggestion that you make establish an possibility for some.
Yes.
Just one will give me why this equation or how this equation is improved.
Oh, this cancellation, everything cancels. That is also basically this I and I prime, if you look at them, they are basically the m minus m prime that I had in the left hand side of the optical theorem equation or the unitary equation, right, in terms of the scattering amplitudes. So that is what, when I am writing the Bhattacharya equation in this form, this is sort of my, because this term also has a extra minus sign in it. This is actually m minus m star term that I had in the optical theorem equation. So I am computing the right hand side, which is giving me whatever I am getting. That is what I am computing, and then I am saying that this is equivalent to that optical theorem equation, and that is valid for unitary theories. So in that case, this will also hold, and we will get a correlator which can tell you whether it is, by looking at whether it is 0 or not. You can comment on this later. Yeah, this is probably clear from this description of the largest time equation. Then you start from a, because again I made this all circuit things as a complex conjugation of the all uncircuit diagrams. This you can think of M and this as next start. Not particularly. Yes.
So then, in that case, this relation with immediately seems to be lost. So in this case, of course, you can say suppose. So in this case, instead of n points, you can say 4 points. In that case, you want to think of it as a good final. Yeah, that time there is some advantage. Here you setting up seem to be that since the relation of basically
Actually, yeah. No, actually, this is I try to motivate from this kind of optical theory. The final thing will be again this thing that I mentioned, that when we go to the average difference basis, then a particular correlator which goes to 0 will be a result of unitarity, or this kind of thing will come in. And if that goes to 0, by looking at that particular thing, you can basically by studying that average difference, or difference correlator is called difference correlator, then that particular basis, whether it is 0 or it has other fluctuations around it, only by looking at that you can comment on the individual. So difference correlator in open systems is a measure of it. This is a way to basically go towards, this is the rules through which, first this is a nice tool, because when you want to deal with Feynman diagrams in open quantum field theory, you also want to be able to deal with anti-time ordered situations, out of time ordered situations, and so on. This will, all of these come handy there. But ultimately you have to study this difference correlator, and what Feynman diagrams you get there, whether all of those diagrams that you particularly get in that difference correlator, whether those diagrams sum up to 0 or not. Because in the difference correlator also you have time ordered, anti-time ordered, and all such kind of terms. You have to take such propagators and see whether the sum of those diagrams go to 0. That I will discuss later. these first came into picture while Proust and Whitman described the same things. I think the Katkovsky rules are probably not the best way to check unitarity for electroweak interactions or spontaneously broken gauge scales. So in those situations, they came up with this rule. So I'm not completely sure how they come into use, but in that concern only this Whitman rules were generated extra from what we already knew from Katkovsky. In fact, for these rules, they got the Nobel Prize for electroweak interactions, scattering and producing electroweak interactions and such. Basically, they checked that this unitarity is valid order by order for electroweak interactions as well. It's not any spontaneous, not any, but particular spontaneously broken gauge scales.